So this is the last slide that we visited before discussing the control. And this is the full data path, giving all the instructions that we wanted to support and all the resources that we needed, all the data steering that we needed to do. And what we wanted to do was add control to this data path to generate the control signals that are in blue in this figure. So the first thing that we discuss is that we want to control the ALU. We want to generate a control for the ALU, and we know that given the instructions that we want to be able to execute, the ALU has to be able to do ANDing, ORing, addition, subtraction. It needs to pass input B, and it needs to do NORing. And this is in support of three groups of instructions. One, the loads and the stores, in which the ALU needs to add because we need to construct that address based on the immediate field and the base register. It also needs to subtract for the branches because that's how we're going to detect equality for the branch on equal. And then it needs to do any other arithmetic and logic instruction that are of the register type. But these 6 functions of the ALU is going to cover all of it, aided by an additional field that comes from the LDUR instruction, which is the function code. But mainly, this functionality can be decoded from this control functions that we are assigning arbitrarily. And then what we need to do is provide the ALU that is going to be looking at this function opcode field with 2 additional bits that are going to tell the ALU which group of instructions we have, the loads and the stores, so that's the same, the branch, or the R type. If it's the R type, then this control function is going to look additionally at the function code from the instruction. So this becomes the truth table for the combinational logic that is going to be the control of the ALU. It's going to take as inputs these 2 bits here that are going to come from the main control of combinational logic, and is going to look at the opcode field and generate the specific functionality for the 6 functions of the ALU. So this is the output. So this in essence is a truth table where we have this many bits, these 2 plus these ones as inputs, and we have 4 bits as outputs. So that is going to be the subcontrol for the ALU. The main controller is going to be generating these 2 bits plus all the other control lines for the data path. And the truth table for that main controller is going to be this one. Here we have all the outputs of the main controller. So you see here the 2 bits for the ALU is going to have the branch detection, is going to decide whether the memory needs to be read or written, is going to signal whether the register file needs to be written, and then is going to do data steering with these additional signals here. The input of this truth table, because all these are outputs of that combinational logic, the input is going to be the opcode of the instruction. Essentially, this is the input, which we are just labeling, but from the opcode, we can tell whether we have an R format instruction, whether we have a load, a store, or a branch. So this is the, and here we have a note that there is a typo in the book for this figure, which is 4.14 in page 274. But the opcode is going to tell us for the main controller which type of instruction we have. So that becomes the input to that main controller combinational logic. And when we put that together, you can see here, this is the first ALU controller that we have. And you can see that one of the inputs is the 2 ALU bits from the main controller. And also part of the instruction, which is going to be the function code. And then it generates the actual functionality that the ALU needs to exert. And as we saw in the previous slide, the main controller takes the opcode. These are the bits of the opcode that comes from the instruction. And it generates the other, it generates the ALU bits and all the other control functions. As we mentioned, this is a data steering control for that MUX. Here we have the branch detection signal. So this basically is saying if we have a branch instruction and the inputs of the ALU subtracted are 0, then we're going to take the branch and we're going to steer the next value of the program counter to be the calculation of the branch target. We have all the control signals, the memory read and memory, the memory read signal, the memory write. This is a data steering, which says, do we take into the second input of the ALU the second register, or do we take the immediate field? And here we have the last control signal, which is forcing the register file to be written. So this is a complete data path so far for the processor, a single cycle implementation that can deal with all the handful of instructions that we talked about at the beginning of the chapter. This is going to be your lab number 5. In lab number 4, which for some of you we're going to talk about today, it's going to be pretty easy. It's just going to be doing the ALU. And then you're going to use that in lab number 5 to do all of this. So let's look at how the R-type instruction navigates through this data path with control. Some parts of the resources here are shaded, and the shaded ones are the resources that are not used by the R-type instructions. And we said that an R-type instruction from a launching register to a capturing register perspective, the launching register is the program counter. That's where everything starts. And the capturing register is going to be the register file, the register that we're going to write. So here we go. We have the program counter with some instruction memory address. It presents that address to the instruction memory. The instruction comes out here. Immediately, immediately we present the first register, because we know we always read that first register, so that's hardwired to the register file. But to know what we present over here, we need to know this signal. So the control is going to generate that signal, and for a register instruction is going to be this field over here. So that's going to show up as the address of the second register. And at that point, the contents of these two registers come out here at the outputs. Then this signal, ALU SRC, is going to steer that output through into the ALU. So we have the two registers that we're going to operate sitting over here. In the meantime, the controller also decoded the instruction and generated the right ALU up bits to tell this subcontrol logic that it is a register type, and therefore it also needs to look at the function code that is coming into here. So this logic is going to generate the right instruction for the ALU. And at that point, then we get the result. And the result is connected to this input of this MUX, which also the main controller, by decoding the instruction, set to it being such that this is the input that goes through. And now we get the result of the instruction back over here in the write data port of the register. Also from the instruction, we have gotten the right register address for the destination register right from the instruction. And then when we have that, also the main control has asserted the register write line for the register file, and when the next clock comes, this data is written into that register, and we have completed the execution of a register type instruction. At the same time that this register is writing the result, we are reading the next instruction. So that is the execution cycle that happens within one clock cycle for this single cycle implementation. You need to be able to explain this like in these terms to understand it enough that you can walk through it. And this is a pictorial view of that. So we get the instruction. So when the clock comes, remember that the next instruction is sitting over here that was generated by just adding 4 to the program counter. And here we're reading the instruction. That's the second register. And the output of the ALU coming through back into the right register port. And so forth. These are the pertinent control lines that are involved. That tells this MUX that this is what needs to be read, comes from this field of the instruction because it's a registered instruction. Sometimes the second register comes from this field, and we need to grab it from here. This is the ALU source, which tells us that we are taking that second register from that second input of the ALU from the register file, not from the immediate field. This is the control, again, that tells us that we are bypassing the memory because it's a register instruction. And then finally that we are writing the register because it is a register instruction and we have a destination register. And obviously the other control lines are not used, are basically ignored during this instruction. They are typed. Now let's look at the same thing for the load register instruction. Here we have shaded what we are not using. Of course, we're not using this part. This part deals with computing or calculating the branch target address. So this is not a branch instruction, so we're not using that. We're also not using the second register because the load and the store only has one read register involved. It does have a write register because we are loading, but we are not writing to the memory. So that's shaded over here. So let's look at that, how that works. Again, we read the instruction that has been just calculated, being the next instruction. And again, we decode the opcode. We always have that first register involved. That's going to be the base register. But now what we do have is an immediate field that comes from the instruction. And we sign extend that immediate field. And now that goes into the second input of the ALU. So we can add it with the base register that is over here and form the address that we're going to read the memory. So we read the memory. And we take this input back to the write data port of the register. Again, from the beginning of the execution of the cycle, the write register address is sitting here, waiting. And at that point, basically, we have done a load. Once the clock comes and we write the register file, we have a load. Let's look at the branch. For the branch, we're going to have that address of the program counter that we're going to calculate the next address as if we're not going to take the branch, but we also are calculating the branch target. We're going to be calculating that from the program counter plus this value over here that we're going to construct from the immediate field. So we read that instruction. We know that for the branch, we're going to be using this field as the second register because we're going to be comparing registers 1 and register 2. So that's what goes into this port, this read port. We're not using the writing because the branch doesn't write. And we're not using the memory or the ALU result. We're using the 0 flag. So here we have the immediate branch target, which is relative. So we're going to sign extended, shift by 2, because the address is in byte. So we have 32-bit instructions with 4 bytes each. Therefore, we need to multiply by 4, which is shifting by 2. We add that to the present value of the program counter, and it sits over here. We still don't know whether the branch is taken or not, so we have not decided which one we're going to be using. If the branch is not taken, we're using this, the very next value, the very next instruction from the present one. If the branch is taken, of course, we're using the branch target address. So once we have the comparison done of these two registers, if we have a 0, and of course we have a branch instruction, which this control has decoded, then we enable the path to be this one instead of the next sequential instruction. And now we have the next address ready to be loaded into the program counter when the clock comes, the clock edge comes, to read the next instruction at the right place in memory. All right, so now I want to add another instruction that we hadn't talked about. I want to add an unconditional branch, and this is sometimes called a jump, but in the RISA, it is a B, unconditional branch, and it has the opcode and a longer immediate field. The type of addressing mode that this instruction uses is by concatenation with the top 4 bits of the old program counter. So this is a 26-bit field. And that's the most we can have because we need these bits for the opcode. So we need to add another control signal to detect this instruction. So now we can add another control signal over here to our table called unconditional branch, and when that signal is asserted, we're basically going to use the concatenation of the upper bits of the old program counter with the immediate field. So if you have seen, the issue with having a single cycle implementation is that you are penalized by the longest path. So you have to figure out which is the instruction that uses the most resources, and that is going to set your clock rate, because you have to accommodate that instruction. That is called the critical path of any digital design, and in the case of this data path, is the load instruction, because you always have to read the instruction, you always have to read the register file, you have to calculate the address, but you have to now read the memory and then write the register file. So it uses all the most resources of any instruction. So we need a way to improve that. Now, one way to improve that is to use variable CPI, an implementation that uses a variable CPI, and you have seen that in your lab number 3. Some instructions took more clock cycles than others, depending on the specifics of the instruction. And since you are going through a sequence of micro steps to execute any given instruction, your controller is more complex. It requires a state machine controller. It's not combinational like what we're using in this single cycle. But you can just for one, you can run at a higher clock rate because now the clock rate is not set by the longest instruction, it's just set by the longest microstep that you have broken your implementation into. So in essence, in your lab number 3 would be a state transition. So that's one way of doing it, and is used mainly. Still, many microcontrollers use that approach. But a better approach is what is called pipelining, which basically you are getting the best of both worlds. Your control still looks combinational, as if it was a single cycle, but you're still breaking the data path in chunks or micro stages, which are called pipeline stages. And then you have registers in between the stages. We're going to look at that at a lot of, we're going to look in a lot of detail at the pipeline, the implementation of the ARM. But we're not going to look at a multi-cycle, which is what you have in lab 3. So let's look at pipeline. What is the idea? Okay. And it's easy to explain it with something like doing laundry. This analogy is used a lot. Okay. Let's say that you are doing laundry and you're doing consecutive loads of laundry. So the analogy is that a load of laundry is one instruction. And each instruction has these micro steps that I referred to. So that's equivalent to the different steps that you have to do to complete a load of laundry. You have to wash, you have to dry, you have to fold, and you have to store. Let's say that those are the 4 steps. Okay? Equivalent to, let's say, reading the instruction, reading the register file, computing the result from the ALU, reading the memory, and writing the register file. So those are the equivalent sort of steps that we have in the ARM data path that we saw. So for the single cycle, we're doing all the steps in a single clock cycle. So this length of time would be your clock period. So you do all that in sequence within a clock cycle, and then you do the next instruction, and you do all of it. Whether you did it or not, the time is there. You have to accommodate the longest sequence. So maybe for some loads of laundry, you don't have to fold, but you still have to accommodate that time of 4 slots, because maybe the next one you do have to fold. So you cannot just change the clock cycle midway. The analogy of the multi-cycle would be that this is a clock cycle. You still have a higher clock cycle or clock frequency, and then maybe for one load you only use 3 cycles, for the other one you use 4, and maybe for some you only have to wash and dry, so you use 2. That's the multi-cycle. But the pipeline concept is that you still keep all the resources available and open, but you keep them occupied at a higher clock rate, which would be a single slot here, and you keep all the resources busy on every clock cycle. So now you have a higher clock rate because your time frame here is shorter, but you're doing everything in every clock cycle. Whether you need or not, you have to have the accommodation for it. So this requires duplication of resources, but they're always busy. The idea is to keep them always busy and superimpose in time So the analogy here of the duplication of resources is that now here a single person could go and do each step, and then that person goes and does all 4 steps. Here you need one person for each task, because in every slot you're going to be washing, you're going to be at the same time drying, folding, and storing. So let's say that you need a person to supervise those steps. So it requires duplication of resources, which is fine. Because that's just more transistors, and we can put lots of transistors on the chip. Now notice that still, if you look at one specific instruction, it still is going to take this much time, just like it was taking here. But what you're getting is a higher throughput, which is at the rate of completion of the task. If you look at a single load, it still is going to take 4 units, and we call that the latency. But after we get through that first one, every smaller step after that, we get the completion of one load. So if we look at a group of loads or instructions, we get 4 done in this many time units, and in this one we had to wait longer. So if we can sustain that throughput, that rate of completion, that's very beneficial from a performance perspective. Usually, if you look at it and ignore the startup latency, the speed up that you get is the frequency of the single cycle multiplied by the number of stages by which you have broken the data path. So if this is running at, let's say, 1 gigahertz, this processor can run at 4 gigahertz. Notice that this calculation over here is not taking into account the sustained throughput. It's taking into account the startup latency penalty, and that's why you don't get 2, you get 3.5. But if you look at it much later, when you have had a sustained rate of completion, then it converges to A divided by the number of stages, which is 2. So this should is going to look like 2. So let's construct our pipeline version of the ARM by breaking the data path into stages. Just like I said, we're going to have the first stage, and we're going to call that instruction fetch. And you know what that does is going to be reading the instruction from memory. Then in the second stage, we're going to be doing the instruction decode and reading the register file. Whether we need it or not, we still don't know which instruction we're going to be executing, but we have the fields from the instruction because we already fetched it. So we can do some speculative reading and of the register file while we are decoding the instruction and figuring out what is it that we really need to do. After we do that, then we have a stage called the execute or calculate the address, because we either have a register type instruction that we need to execute, or a load or a store or branch that uses the immediate field, and that's sort of the calculation of the address. Then we need to access the memory. Now, if we have a register type instruction, as far as that instruction is concerned, nothing happens in this stage. It's just passing it through. But if we have a load or a store, then that's where we access the memory, because we calculated the address here in the previous stage. And then we write back the result to the register file, whether it came from the execution because it was a register type instruction, or whether it came from memory in the case of a load. So we are going to break our pipeline into 5 pipeline stages. So ideally, we should be able to run this implementation 5 times faster than the single cycle and get 5 times the performance improvement, and that's wonderful. So this is an example of the different stages that are required for the different instructions that we looked at. So the branch requires the fetch. They all require the fetch, of course, and the instruction decode and the execution, because after the execution for the branch, we know if we're going to take the branch. But in pipelining, you still have to go through all the stages. So it's, from a control perspective, it's simpler because you go through all the stages as if it was a single cycle. If you start short circuiting, now you have to remember things, and now you introduce a state machine, and you can no longer have combinational control, which we can have here in the pipeline. As you'll see, all we have to do is send it down the pipeline, the control signals. The add instruction doesn't require the memory, but requires the execution and then the write back to the register. The store doesn't require the write back because we're just storing in the memory. And as we saw with the single cycle, the load is the one that utilizes all the resources, in this case, all the stages. So we fetch, we decode, we calculate the address, we read from memory, and we store it in the register. And these are some actual numbers that we can assume for the stages. And of course, the pipeline implementation is such that we set the frequency, for simplicity, we set the frequency of the clock by the period or the delay of the stage that takes the most time, because we want to have a fixed frequency design. What that says is that it's important to balance the delay of the stages. One of the crucial things of designing a pipeline implementation is balancing the delay of the different stages so they are about the same. Because if you allocate most of the delay to one stage, you have to set your frequency by that stage, and you don't gain a lot of improvement. So the assumption is that you can, when we say you can take the frequency of the single cycle and divide it by the number of stages, the implicit assumption there is that you are balancing the delays of the stages, and each stage has about the same delay. Which in this case, when we say about the same, 200, 100 picoseconds, it's a factor of 2, but you may not be able to do better than that, given that some logic blocks are monolithic and it's not feasible to break them up. So here we have the different delays of the steps and how much actual delay an instruction takes. So we can see that as we said, the load takes the most time, utilizes all the resources. So say we take 200 picoseconds to read the instruction memory. We take 100 picoseconds to read the register file. The ALU takes 200 picoseconds, memory access takes 200, and register write takes 100. So this gives us different delays, but the worst case is this one. So let's look at that with the 800 picoseconds. And let's see how we can improve that. Obviously, you can see how that can be improved by superimposing the different steps. So just to restate what I just said, if the stages are balanced, then we get the an improvement that is the same as the number of stages, and if not, of course, you're gonna get less speed up. We talked about latency, so let's go on. All right, so on to pipelining, the subset of the ISA that we are looking at, and highlight the things that make this ISA conducive and friendly to pipelining. So first of all instructions are the same number of bits. So 32 bits, that's one instruction. That makes it easy to fetch and to decode in a single clock cycle between pipeline stages. Not all processors are like that. For example, the Intel processor has a variable length instruction ISA, which some instructions can be as few as 1 byte, where some can be 17 bytes. And that introduces complexity because you need to start getting the instruction to figure out if you need to go back and get more of the instruction, because you never know how many bytes exactly the instruction is. So it adds complexity to the instruction decoding. Also, if you have a few and regular instruction formats, it makes it easy for decoding, and also you can make assumptions and hardwire some things, such as reading the register file. We know that first register is always read, and that field is always that first register in the register file. So we can just hardwire it. The fact that our only interaction with memory is through loads and stores simplifies the design, because we can calculate this address in one stage and then access the memory in another. So these are several aspects of the elegance of the ISA that make it easy to pipeline, and therefore to improve the performance. The other thing about the ISA is that memory is aligned, and therefore we can have a memory that can be read or accessed in a single cycle. So that helps the performance as well. Now, what makes pipelining hard? And we're going to talk about these issues. Hazards. Or this type of issue collectively is called hazard. And there are 3 types. So we're going to talk about how we tackle each one of them. Starting with the easiest one. The easiest one is what we call structural hazards. And that is when there is a collision or competition for the usage of a resource. So let's say that you wanted to use a single ALU to calculate the next value of the program counter and also use it for everything else. Well, you may not be able to do it with a single ALU. And I say that this is the easiest type of hazard to deal with, because if you have competition for a resource, all you do is replicate it. So you throw more resources, more hardware, and that's fine. And you get rid of that hazard. The second type of hazard is the one called data hazard. And that is when you need to utilize in a given instruction. Remember that in each clock cycle, only part of the instruction is being executed because you have these steps for each instruction. The programmer, remember, doesn't see that because this is an implementation issue and the programmer just sees the instruction. That is the view, the abstraction to the programmer is the ISA. It doesn't see these micro steps. But if the instructions are one after the other, for example, let's say that you are adding 2 registers and putting the result in register 10, and now you want to use register 10 in the next instruction as a source register. Well, when you are reading the source register for that instruction, for that second instruction, register 10 has not been written yet because the instructions overlap. So you don't have the data that you need, and you may have to wait. Now, we don't want to wait, because if you wait, then the performance of the pipeline implementation degrades to the single cycle performance. So that's not good. And we put a lot of effort into crafting the stages, and as you'll see, putting the pipeline registers and all that. So we don't want to wait. So we're going to see that we're going to be adding some hardware techniques to deal with data hazards, which are called forwarding. And we're also going to be talking about the fact that sometimes you have no choice but to wait, but you want to minimize that wait. But if you do need to wait, then you need to introduce sort of a bubble cycle in the pipeline, a dummy microstep or dummy clock cycle, sometimes called a bubble, but that action of the pipeline, and you need to generate control for that, that action of the pipeline is called a stall, generating a stall. So we're stalling the pipeline for one clock cycle to allow a previous instruction to advance while holding one that needs its results, so to catch up and we get the right result. So all this spells more control, more complexity, but we can deal with it, and we're going to be seeing that. So that's how we deal with data hazards. And we're going to revisit all of this in a lot of detail later. And then we have control hazards, which are the most complex to deal with, which is when we hit a branch instruction, a conditional branch instruction, we don't know which way to go until much later. But we are ready to read the very next instruction in the next clock cycle, but we may not know if that is the right path until 2 or 3 cycles later. So there is a whole body of knowledge of how to deal with branch prediction and a speculative program flow control. And we're going to be talking about some of that, but those are the most challenging to deal with, the control hazards. Again, that is the fact that we don't know if the next instruction that we are fetching after a branch is the right one to fetch, or the next two. So we don't know which path to follow. And one or two instructions is in the context of this pipeline, which is very short, actually. This five-stage pipeline that we're talking about in this chapter is very short. Normally, pipelines are 9 stages, 11, 13 more. Those type of implementations are called super pipeline implementations, but those are what is used currently. This is just to be able to explain the concept, but it's on the simple and short side. So imagine if you have an 11 or 13 stage pipeline and you have to wait 5 clock cycles to decide which way to go because you are looking at a branch, that is a big performance penalty. So predictive branching is a big field in computer architecture and organization. But we can deal with them. And again, there are even other issues that we're going to be talking about later that are even more challenging in pipelining, such as interrupts and things like that. But for now, let's just concentrate on these three.